Welcome back to calculating probabilities, conditional, mutually exclusive, and dependence, intersections and unions using specific values and determining these probabilities. Felicity attends Modesto Junior College, and the probability that Felicity enrolls in a math class is 0.2. The probability that she enrolls in a speech class is 0.65. The probability that she enrolls in a math given speech is 0.25. So M is math, S is speech, and M given S is math given speech. We know the probability of M is 0.2, the probability of S is 0.65, and the probability of M given S is 0.25. What is the probability that Felicity rolls in math and speech? Well, we're told the formula, general multiplication formula. That means that I need to take 0.25 times 0.65, and I get 0.1625. What is the probability Felicity enrolls in math or speech? General addition rule. I add the math plus the speech and subtract anything that they have in common so that I don't double count. Then I get 0.6875 as that probability. Now, are they independent? Does the probability that she enrolls in math, given that she is in a speech class of 0.25, does that equal the math probability of 0.2? No, it does not. They are not independent. Are they mutually exclusive? Remember, to be mutually exclusive, their intersection needs to be 0. You can't do math and speech. Well, we clearly have math and speech. We calculated that in part A. That is not 0. So no, they are not mutually exclusive. All right, moving on to our next problem. Studies show that about 1 in 7, approximately 14.3, that's rounding, percent of 1 in 7 women who live to be 90 will develop breast cancer. Suppose that these women who develop breast cancer, of those women who develop breast cancer, a test is negative 2% of the time. Also suppose that the general population, the test for breast cancer is negative about 85% of the time. B is breast cancer, N is negative. Talking about a woman in general, let's write out the probabilities that we were just given. Probability of B, and really this should say who lives to be 90, because that's included in the problem. That's equal to 14.3%. The probability of testing negative was 85%, and the probability that tests negative, given they develop breast cancer, is 2%. What is the probability that a woman develops breast cancer? That was 14.3%. What is the probability that a woman tests negative? That was 85%. Given that a woman has breast cancer, what is the probability that she tests negative? Given is always the second part, so I write that first. That was 2%. Now we get into calculations using this information. What is the probability that a woman has breast cancer and tests negative? And is the general multiplication rule where we multiply the conditional probability. So B and N is equal to the probability of B times the probability of N given B. So the probability that you develop breast cancer, write this in percents, times N given B, which is 2%. 14.3% times 2%. If you double 14.3, you get 28.6. But as a percent, you typically multiply as a decimal. This is actually 0.143 times 0.02, which means the 28.6, I need 5 numbers behind the decimal, which is actually 0.00286. And if I wanted to write that as a percent, that's 0.286%. So something to be careful of. The probability of breast cancer or negative, that's the general addition rule where you take the probability of developing breast cancer plus the probability of testing negative in general minus the probability of breast cancer and negative, which we just calculated the intersection. The probability of breast cancer, developing breast cancer, was 14.3%. The probability of testing negative was 85%. And then we just calculated the intersection as 0.286%. 14.3 plus 85 minus 0.286 gave us 99.014%. Are having breast cancer and testing negative independent? Is the probability of having breast cancer equal to the probability of having breast cancer given that you test negative? Another way you could say that is the probability of testing negative equal to the probability of testing negative given that you have breast cancer. And the reason I switched it is because we know this piece of information and this piece of information. Negative was 85%. Negative, given they have breast cancer, is only 2%. So no, they are not independent. And you wouldn't think so logically either. Are they mutually exclusive? Can you test negative and have breast cancer? Yes. You would do that 0.286% of the time, which is not zero. All right, moving on to our last question. Going back to this problem that we just worked on, P is testing positive. So recall that we had the probability of being negative was 85%. The probability of developing breast cancer was 14.3%. The probability of testing negative given you had breast cancer was 2%. We calculated the probability of testing negative and having breast cancer to be 0.286%. Let's see what else we need here. Given that a woman develops breast cancer, what is the probability she tests positive? So we want to know, finding the probability of testing positive given that she has breast cancer. That's equal to 1 minus the probability of testing negative given she has breast cancer. We know that testing negative given she has breast cancer is 2%, so that's going to be a 98%. So 1 minus 2%, or 100%, minus 2% is 98%. What is the probability that a woman develops breast cancer and tests positive? So now we're given some hints as to calculate this. We need to take the probability of testing positive given you have breast cancer times the probability of having breast cancer. The probability of testing positive was 98%, or 0.98 if you're multiplying, times developing breast cancer, which was 14.3%, which gives us 14.01%. Or 0.14 if you're doing this as decimals. They both, you can multiply, it's better to multiply as a decimal to keep the decimal number equivalent. What is the probability that a woman does not develop breast cancer? So we're finding the complement. The probability of not developing breast cancer is 1 minus the probability that she does develop breast cancer. So that's going to be 100% minus 14.3%, which is going to give us 85.7%. Then what is the probability that a woman tests positive for breast cancer? That is going to be the probability 100% minus the probability that she tests negative. So 100% minus 85%, which is 15%. All right, thanks for joining us as we explored probability.